we've just had an informal discussion about how priority queues can be used for sorting, but we didn't look at all of the details. So now let's use pseudocode as a tool to truly look at all of the details and make sure we understand how different flavors of priority queue may perform under slightly different circumstances. Okay, the worksheet that I'm going to be working through is broken down into two pieces. First off, there's the actual pseudocode that we'll be analyzing, and this is in a pretty common format for pseudocode. So let's briefly talk through it, and then we'll work through one of the questions down below. And there's already a table out here to the side to help facilitate working through the questions. So I'm going through this on paper to kind of model the process. I think it's beneficial to actually print out the worksheet if you can and work through it on paper as well, although working through it with a PDF reader or something like that is also fine. Okay, talking through the algorithm. So we define the algorithm. It's a PQ sort algorithm. It's got a parameter called S. The input S is a list of items of type E, and the output is S as it's sorted. And now we've got the main body of the algorithm. It's going to create a priority queue. It's got a while loop that will loop until S, the list, is empty. It will get the 0th item from the list. It will remove the 0th item from the list, and it'll insert that 0th item into our priority queue. So that's the first loop. The second loop then goes until the priority queue is empty, and it extracts the minimum item from the priority queue and adds it back to the list. Okay, down below there are a couple of different questions. We'll work through the first one in this video, and the remaining 3 you should work through on your own. So the first question is, well, the questions in general, estimate an upper bound for sorting n items. So this is purely about an upper bound, and we'll be just a little bit sloppy with how we compute it. If we go through rigorous analysis and limit tests, we might be able to find a slightly better estimate of the upper bound. So question 1, it says the priority queue is an unordered linked list. Now, underline that because it seems important. And the list is a linked list. Oh, so this is one of the things that our previous approach overlooked. We didn't think about how data was actually being stored other than the priority queue itself. So one of the benefits of using rigorous pseudocode is to incorporate details like this that could have a significant impact. And in fact, in some of the remaining 3 parts, you'll see that this choice is really, really significant. Okay, so in order to do my estimate here, I'm first going to go through and look for kind of big picture things. So we've already talked about this before. It's going to iterate through this first loop until the list is empty. And we're going to consider it to be n, our problem size, the number of items in our list. So all of the things that are taking place inside of that loop are repeated n times or fewer. The list is getting smaller and smaller, so this loop will actually iterate exactly n times. In some cases, we can come up with an upper bound really, really easily, but there may be a more precise choice than our initial easy first estimate. Our second loop, again, is going through the priority queue, and it's continually extracting items and adding them to the list. So we'd added n items to the priority queue, so we'll have n items to remove from the priority queue. Okay, so I've got a column here to help us identify the important things for problem 1. So I'm first going to focus on priority queue operations. So we've got an unordered linked list as our priority queue. I'm going to assume that creating that is constant time. So this line is the first line of code where we see the priority queue being used. I'm also going to look at the other places where the priority queue is being used. So we're doing an insert into the priority queue. If you remember the unordered linked list, it's not ordered. We're just strictly tacking things on to our list. So I'm going to put a 1 there. It's a constant time operation. Our next loop, we're continually checking to see if it's empty. We can make an argument that there's a way to do that in constant time. We're extracting the minimum, and again, this is where the unordered linked list does poorly. We have to look at every possible item in the list. So initially, we'll have n items in the list, and we'll have to look at all n of them. And then after that, we'll have n-1 and n-2, and so on. But we can pick n as an upper bound. Again, it's slightly pessimistic, but we're just trying to do an initial estimate here. Okay, so at this point, I've taken care of all of the priority queue operations. Now let's go ahead and deal with the remaining lines, which are primarily about the linked list. So the list being used is a linked list, so checking to see if a linked list is empty. we should be able to do that in constant time, getting the 0th item from the linked list. Now, this is where we have to be a little bit cautious. Generally, a get operation on a linked list is order n, but in this case, we're getting the very first item, always getting the very first item. And that's always going to be exactly one operation. Basically, our head pointer will point to that very first item. And then we're removing the 0th item. So again, it's an index-based operation, but it's a special case of the index-based operation, and we can argue that it's constant time. Okay. Finally, our last line down here, we're adding something to the list. So this is appending to a linked list. If our linked list has a tail pointer, that is also a constant time operation. So by the way, I've made some assumptions about the way my linked list behaves there. So I'm assuming that my linked list is a doubly linked list, or at least has a tail pointer. So I'm going to go ahead and jot that down here. Okay, now we can go ahead and compute our totals. So I'm going to be more rigorous about this than I've been in some of my previous examples. So we've got n times several constant time operation, 1, 2, 3, 4, 5 constant time operations. And then in our loop down below, we've got n times 2 constant time operations and an n. And then I'm going to go ahead and simplify 5n plus 2n plus n squared. That's 7n plus n squared. But at the end of the day, the n squared really controls the growth here. So I'm going to simplify this to n squared. And we've got an estimate. Again, this is maybe more pessimistic than reality, because our loop here, we're assuming that every extract min is order n. But after we've started removing things, the list gets smaller, and it'll take a little bit less effort than n. Okay, and just kind of a final reminder, the unordered linked list is basically a variation of our selection sort. Okay, with that, I recommend that you work through the remaining 3 parts yourself. So these are variations of using different priority queues and the linked list versus the array list.